Okay, so today, as well as Tuesday and Wednesday, we are going to work on solving trig equations. We don't have enough time today to get through all of the types of examples, so we're going to start out with just the basics of solving trig equations, and then when we come back from our 3-day weekend on Tuesday, we will look at some more involved examples. Okay. Here's a trig equation. Sine of x equals 1/2. Okay. Our job is to solve for the angle x. Okay. And our knowledge of graphing in the unit circle is what's going to help us. So, when does the sine of x equal 1/2? Pi over 6? Anywhere else? 5 pi over 6. Monique has kind of an inflection in her voice. Maybe she's not sure.
Confidence money.
Well, is she right or not?
Yeah.
Okay. So at pi over 6 and at 5 pi over 6, are those the only places?
Yes.
Are those the only places? No. If we think about this in a graphical sense, okay, sine of x is a graph that we know has a domain of all real numbers, so it goes on forever in both directions, right? So if we think about the line y equals 1/2, where do they intersect? Well, you said pi over 6 and 5 pi over 6, but then it happens in the next period, then it happens in the next period, and then it happens in the next period. Okay? A lot of you are picturing the unit circle, right?
Yeah.
Oh, I am struggling today. There we go. Okay, here's our unit circle. Here are the two places you were picturing of where the sine of x equals pi, or where the sine of x equals 1/2. But if we think about it, are we restricted to only rotate once around the unit circle? No, we could rotate here to 13 pi over 6, and then we could rotate again to 25 pi over 6, and we could keep rotating and rotating and rotating and rotating. So it doesn't matter if you think of the unit circle or if you think of a graph, but there's going to be an infinite number of solutions to any trig problem that I give you, unless it's undefined. Okay. So we're going to have to think of where it occurs on the unit circle, but then also keep in mind that our graph is going to extend and have multiple periods, and so we'll have to figure out a way to express our answers. What's the period of sine of x? 2 pi. So do you agree that this solution right here is going to repeat every 2 pi?
Yeah.
And this solution right here is going to repeat every 2 pi. Okay. So when we get to the point where we have something like this, we can think about where on our unit circle that happens, but then we have to keep in mind that it is going to repeat every period. Okay? And I'll show you how I want you to notate those answers. Okay? First, let's talk about how do we get something to look like that. Okay? Do you think that's going to be the equation I'm going to give you? Okay, so I'm going to give you something that's a little bit more complicated. Okay, your goal is to isolate a trig function. So if it's linear, that's that's going to be pretty simple, okay? If it's a linear, what do I mean by linear?
Line.
Okay, what kind of power?
1.
Okay, 1. A linear equation has a power of 1. So if your trig function is just to the first power, okay, because we've seen trig functions to more than the first power, then you can isolate that trig function to where it looks like sine of x equals 1 half. Okay. If you don't have a linear function, then you may want to try to factor it. But remember, we can only factor if our equations are set equal to 0. Okay. Now, these are more the types of problems that we will look at on Tuesday. Okay. Some of the nonlinear types of problems, especially these right here, we still may need our identities. I'm not saying that you need to use your identities every single time, but there are going to be situations where you're going to need to reference them. Okay. Then we need to write our complete solutions, and this is how we're going to do it. You are going to write the solution, and then plus whatever the period is times n. I'll let you write it down, and then I'll go into more detail about that. Okay. So if this were our equation to solve, okay, you would express to me two different answers. I know that there are an infinite number of solutions, but that's not what you're going to write, infinite solutions. Okay, there's a way to express those infinite solutions. So what you're going to do is you're going to identify the places where this happens. Sine of x equals 1 half at pi over 6. And 5 pi over 6. And since sine has a period of 2 pi, you are going to write on each of them plus 2 pi n. N is representing any integer. Okay, 1, 2, 3, 4, 5, 6, maybe 1, 2, 3. Okay, so what's happening is pi over 6 happens, and then 2 pi later it happens, and 4 pi later it happens, and 6 pi later it happens, and over and over and over again. So we have all of these solutions happening, but since there's a pattern, we can express them this way. Does that make sense? Okay. I also want to point out that these would be our complete solutions. Okay. There are times where I could ask you for just the solutions between 0 and 2 pi. But if I ask for the complete solutions, that means you're writing it like this. Okay? So we're going to do a couple of examples so you kind of get the hang of things. Okay? And then we'll go from there. Write this one down. Okay. Thoughts on what we should do? We need to get sine of x equals something, right? So what should we do with this guy right here? Add it over here. Yeah, we are solving an equation. When we talked about trig identities, was it an equation? It was not. I had an expression and an expression, and I was asking you to prove that they're equal. Now I'm giving you an equation that I want you to solve. Solve implies equation. Okay? So we can add sine of x to the other side. Then what? We can subtract radical 2. Last step. Divide by 2. Okay, we have now isolated our trig function. What? It looks familiar? Okay, where does this happen at? Negative radical 2 over 2 happens at 5 pi over 4 and 7 pi over 4. Guess what? You're not done with the unit circle, are you? I told you you wouldn't be. Okay? So, the sine of x is negative radical 2 over 2 at 5 pi over 4 and 7 pi over 4. But we know this repeats every period, so we're going to write plus 2 pi n to describe those complete solutions. And this is your answer. What do you think? Not too bad yet? Okay. Really, the catch more comes on Tuesday. Today, we're keeping it simple. Keep it simple, Sally.
Mr. Cooley says keep it simple, stupid.
Oh, yeah, I don't like that word, so I will not use that. All right. This one looks a little bit different. More fun, because there's, well, it's not really double, it's squared the amount. Okay? Now, we'll get into, on Tuesday, opportunities to factor our trig equations. But since we still only have one trig equation, even though it's squared, if there's only one term that has that squared function, we can still isolate it. So think about how you would solve the equation for x squared minus 1 equals 2. How would you solve that? You would add 1 and then divide by 4, wouldn't you? Well, let's do that. Let's add 1 and divide by 4. Then what would you do? Hold on, Riley.
Well, couldn't you do like a trig or identity with cosine squared x minus 1? Or is that not allowed?
Well, you could with cosine squared minus 1, but you cannot with 4 cosine squared minus 1. Like that 4 is attached to the cosine squared, so it's not cosine squared minus 1. But that is a good thing to keep your eyes out for. Okay, but since that 4 is attached, we cannot. Okay, now what would we do to get cosine by itself?
Square root.
We would square root both sides. I need you to remember that when we square both sides, our answer is positive, negative. What's the square root of 3? Square root of 3. What's the square root of 4? Oh, that's a familiar number. How many answers are we going to have to express?
4.
Man. Okay, so the cosine is a positive radical 3 over 2 where? Okay. Ooh, I like pi over 6 today, huh? And it's a positive at 11 pi over 6. Okay. Cosine is a negative radical 3 over 2 at 5 pi over 6 and 7 pi over 6. And since cosine's period is 2 pi, we're going to add plus 2 pi n to each of these. Okay, now I do want you to keep in mind that the back of the book is going to condense answers as much as possible. So this is what I would really want to see, but I am going to warn you that in the back of the book, they're going to see this. They're going to see, oh, I have 4 answers, but these 2 answers are pi apart. So I could write these as pi over 6 plus pi n, because then I would get all of those answers into just one expression. Oh, and over here, these 2 are also pi apart. So I could write these as 5 pi over 6 plus pi n and be able to express all of those answers into one. Now, I don't expect you to do that, but I just want to warn you that the back of the book will do that in the case where all 4 answers are present. They'll squish them together to 2. Do you see what I mean by that? Okay. I don't really want you to do that. If you do it, it's fine. But I'd rather see all 4 separate. Okay? I just want you to I want to warn you about that for when you're checking your answers. Okay? One more and then we're done. Okay? And you, guess what? Did you even look at your gold sheet? Do you know how many problems you have for your homework?
3.
4. And these are way shorter than your trig identities. Don't you agree? Okay, third and final example.
7.
Okay. What should we do? Addition. Add that radical 3 over. And then we have the cotangent of x equals radical 3 over 3. Some of us feel uncomfortable with reciprocal functions when it comes to the unit circle. Okay? You can either suck it up, or if you really need to, you can think of this being the same as the reciprocal. The tangent of x is radical 3. If I take the reciprocal of both sides, then that's okay in an equation. Okay? So the cotangent of x equaling radical 3 over 3 is the same thing as the tangent of x equaling radical 3. Okay? Well, where does that happen?
Pi over 3.
And?
4.
period of tangent and cotangent? Plus pi n. Okay, now one more thing to talk about here. What's the distance between pi over 3 and 4 pi over 3? Pi. And we wrote our expressions as plus pi n. So in the back of the book, you're only going to see this answer because this is being redundant. But I don't mind you being redundant. I'll take one, I'll take both. But that's going to happen only in the case of tangent and cotangent because their period is pi. All right, what do you think?
It's all right.
Can you do it? Okay. Okay, well, this video will be on my website if you need to come back. All right? You have 4 problems, and they are not any more complicated. They may be even more simple than the ones we did in class today. Okay?